Today we want to look at integration by parts, but before we look at that, let's take a look at a problem from the homework, which was very similar to the ones we were talking about yesterday. So in this problem, we want to identify the following integrals that yield an arcsine or an arctangent function upon integration after an appropriate substitution. Oh, because I'm in Canvas as me, it just tells you what the answers are. This is how I know. I don't actually know how to do it in calculus. I just read the answers on Canvas. But what we're looking at is we're looking for a substitution. Notice that in the first one, we've got x over 4 minus x squared. This one looks like a regular substitution. W can be 4 minus x squared. dw is something times x dx. So in this first integral, we'll end up with, looks like a negative 1/2 natural log of 4 minus x squared. Oh, natural log of absolute value of 4 minus x squared plus c. Regular substitution. In the second one, the change is not just the plus, but in the numerator, we have a 4 instead of an x. So we don't do the same substitution in the 4 plus x squared. This one is going to give us an arctangent. We're going to have to do some substitution because we haven't integrated 1 over x squared plus a squared. We've only integrated 1 over x squared plus 1, the base version. So that's why b is going to give us an arctangent, because it's 4 plus x squared, and there's no x to be the derivative in the numerator. Part C is like part A. We've got x over the square root of 4 minus x squared. The square root of 4 minus x squared is something that's going to want to make us think about arcsine. But we have the derivative of 4 minus x squared sitting in the numerator. So that tells us we're going to integrate this as a w to the negative 1/2 function. Because we have the inside can be 4 minus x squared, and the derivative of the inside will be the x. Then in the last one, we've got x over the square root of 4 minus x to the 4th. This one looks like the one that we did yesterday with the arctangent. I can't make the substitution 4 minus x to the 4th power because the derivative is an x to the 3rd. And we don't have that. We don't have an x to the 3rd to be the dw. But like we were talking about yesterday, our substitution should be based on what's going to be our dw. In this problem, it looks like we can have an x for the dw. If x is all we have for the dw, then all we can substitute for w is x squared. So this, upon substitution, will look like a constant times 1 over the square root of 4 minus w squared. And that will give us an arcsine. So that's the kind of thinking that we want. And it's all based on the thinking that we were looking at yesterday. What's going to be my dw? That's the big question when you're doing a substitution. Any questions? This is a weirdly formatted question because it's making you thinking about integrals. It's giving you 4 integrals that ostensibly you would just want to compute. But it's not asking you to compute the integrals. So, that makes sense? Yeah. Remember that the question, when you're thinking of doing substitution, it's not only what's my w going to be, the more important question is, what's my dw?
Yeah. So as long as your w yields like the dw somewhere in it, you can just get how you want.
Correct.
So it doesn't matter that that's next to the 4th, it's like square root that.
Well, you wouldn't square root it necessarily. Let's write that one down. So if we have the integral of in this case, we can't go with a w equals 4 minus x to the 4th because we don't have the x to the 3rd. What we have for the dw is just the x. So the way we're going to read this function I'm going to read the x to the 4th as an x squared squared. So I'm just going to break down the x to the fourth as an x squared squared. I'm just going to write it differently. And then I can make w my x squared. And then dw will be 2x dx. And then we can turn this around to get the 1/2 dw. Is the x dx. So the x and the dx are going to be a dw. I'm going to pull the 1/2 because it's a constant factor. The function that we're integrating is going to be 1 over the square root of 4 minus w squared. And that 1 over the square root of 4 minus w squared, that's what's going to produce an arc sine. We haven't learned which arc sine it's going to produce. But it'll be the arc sine of w over 2. So this problem was in coming right after what we were talking about yesterday. What's going to be my dw? That's the important question when you're making a substitution. Any questions? This thinking, and excuse me, this thinking, apparently I'm going through puberty again. This thinking about what's going to be the dw is why I prefer not doing the solve for dx style of integration by substitution. So rather than taking dw dx and solving for dx and putting that back in the integral to cancel out the x's, I don't like that method because it emphasizes follow your nose type process over thinking about what the function is telling you. And I will always favor thinking about what the function is telling you over follow your nose type process. This is why PEMDAS is such trash. PEMDAS is trash because it's trying to program you as if you were some computer and you're better than that. Worse at some things, like large calculations very quickly, but better at everything else. Thinking. Computers are very good at calculating. Computers are trash at thinking. Look how hard we have to work to simulate a computer thinking. Look how long we've been working on the problem. And look how fast a human has to picks up thinking. Just on their own, just by observing. You know what I mean? If you want to convince me that a computer is skilled at chess, you need to show me that all you did was teach the computer the rules of chess and make it play games. If you teach the computer strategy, then you're just trying to make a copy of your skills in chess. Does that make sense? It's learning from the masters. Now, granted, that is how, as humans, we learn from the masters. We read about things and we practice those maneuvers, but we don't get them programmed directly into our head. That makes sense? I got to admit, though, the computer that plays Jeopardy, that's a pretty impressive feat. But think about the hours and hours of programming, the years of programming that I went into building a computer to play Jeopardy. And look how naturally we all just do it. All right. Let's talk about integration by parts. We need to switch gears. We need to grab this anti-product rule. Here's the good news with integration by parts. It's a formula, and we just have to remember it. Here's the bad news about integration by parts. It's a formula, and we have to remember it. Moreover, we can't just blop out a formula and have everybody be proficient in the formula already automatically. We have to practice using the formula. All right. Here's integration by parts. This is an anti-product rule. And this is the way that I write integration by parts. So like simple statements of things. Integration by parts says the integral of u dv is uv minus the integral of v du. The integral of u dv is uv minus the integral of v du. Over on the left, the integral of u dv is the integral that you're given. And uv minus the integral of v du is what it's equal to. That's the side of the formula that you're going to be using. The integral of u dv is uv minus the integral of v du. There are 4 parts. And since Star Trek Next Generation, I can't say there are 4 of anything without imagining in my head, there are 4 parts. Like yelling at some Cardassian torturer. That was a good episode. And for the life of me, I can't remember if there are supposed to be 4 or is it 5. It was 4 lights, right? Yeah. What are we talking about? Oh, yes. There are 4 parts. And then there's the Cardassian. Oh, surely you see that there are 5 parts. There are only 4. The 4 parts are u, v, du, and dv. Those are the 4 parts. We're going to focus on the 2 parts that you're given, u and dv. Those are your given parts. The other 2 you have to find. There are 4 parts. The 4 parts are u and du, v and dv. 2 of the parts you're given. So these 2 parts you're given. The other 2 parts you have to find. Once you decide what u is, it's bad grammar. Once you decide what you are, you differentiate to find du. Differentiate u to find du. And you'll integrate dv to find v. Then all you have to do is put things together into the formula and evaluate your secondary integral. Notice that your formula for parts, the integral of u dv, is uv minus the integral of v du. So once you find your parts, you put things together into the formula and evaluate what I'm going to refer to as the secondary integral. In a way, this is similar to substitution, as we're trading the integral of u dv and the integral, when we do the parts formula, and we have a simpler integral. This secondary integral should be a simpler integral than the one we started with. We are trying to make our lives easier, not more difficult. Right, let's do an example. Here's the kind of integral that parts was designed for. One of the reasons that we do parts after substitution is that with substitution, we can look at what we're trying to integrate and we can see the chain rule right there. Well, at least with the ones that we start with. We can see the chain rule right there. I could see that something was integrated because it looks like sine of x squared times 2x. And we can see that x squared inside and the 2x as the derivative of the inside. We can see that the chain rule happened. The chain rule leaves footprints all over our integrals. Not so when we're undoing the product rule, because we're only getting half of the story. Here's the integral u dv, then the other integral is v du. So we're only looking at half. We can't see the product rule happening here. So it's a different way of thinking. Here's what we want our approach to be. You want to look at an integral and think, is this substitution? And if the answer is no, then think, okay, maybe it's parts. And at this point in your mathematical career, that's where it ends. So we look at this and we see this is not substitution. There is an x squared and a 2x because I'm being a jerk. By putting that 2x in there, you're like, oh, that's the derivative. But that 2x is not the derivative of anything that's sitting inside another function. I wouldn't say that the inside is x squared and then the derivative of the inside is 2x, because the 2x is inside the sign. There's a composition going on and the dw is in the wrong place. So the most important step in doing this integral is to recognize that it is not a substitution integral. First thing to notice, it's not substitution. So the d, if this was an x squared, the sine of x squared, and then the 2x was out here, that's substitution. Because I can make w equal x squared, then dw is over here as a factor. Remember, to do a substitution, we need the dw as a factor. In this problem, if w is x squared, dw is not a factor. dw is going to be inside the sine of 2x, so it's not going to be a factor. So the first step, it's not substitution. Then we can assign a u and a dv. These are the parts that are given. One of these parts needs to be the u, the other part needs to be dv. I'm going to make u equal to x squared And that leaves sine of 2x dx to be the dv. When you split apart your u and v, they have to be factors. This is the integral of u dv, u times dv. U and dv are factors. So I couldn't just pull out this sign by itself because that doesn't mean anything. It's the sine of 2x. That's a factor. X squared is a factor. So we split by factors. So 0 step, not substitution. First step, choose what's u and dv. I just use the word choose. You're going to have to decide which is u and which is dv. That raises a question. How will I know which one is u? The answer is you'll just know. Because you'll try it the other way and it won't work. It'll be really annoying, but that's part of the process. So I made the choice for you where u is x squared and dv is sine of 2x to x. We differentiate to find du. Derivative of x squared is 2x to x. And the integral of sine of 2x is minus 1/2 cosine of 2x. Remember, we're integrating, so the integral of sine is negative cosine. That 2, since we're integrating the 2x, is going to produce a negative 1/2 out in front. Step 0, not substitution. Step 1, assign u and dv. Step 2, differentiate to find du and integrate to find v. Next, put things together in the parts formula. The integral of u dv is uv minus the integral of v times du. So the integral of uv dv is u times v minus the integral of v times du. So a few things are going to happen. I have a 1/2 times a 2. Those will cancel out when I multiply. I also have negative from the formula and negative from the minus cosine of 2x. So I'm going to do this. And we have integral of x cosine of 2x. Any questions? So step 0, it's not substitution. Step 1, assign u and dv. Step 2, differentiate to find du, integrate to find v. Step 3, put stuff together in the parts formula. Clean things up whenever you can. Step 4, integrate your secondary integral. Now I have to decide what technique we're going to use on our secondary integral. Is it substitution? No, you can tell by the tone of my voice that it's not substitution. I would have just said it's substitution. But I'm like, oh, is it substitution? You're like, oh, no. You could have been dead asleep and just woken up at the end of substitution. It's like, oh, no. This is the way I sounded. So the only other technique that we have is parts. Surprise, it was a 2-for-1. Step 4, integrate the secondary integral, and it might be parts again. And at this point, you'll be like, oh, dude, Leach, first example in parts is multiple parts. And I'm like, oh, heck yes. We don't play around up in here. So we'll do the same thing. We'll pick a U and a dv and find du and v, put them together in the parts formula. Not forgetting that we still have this minus 1/2 x squared cosine of 2x. So the secondary is parts again. I'll say u is equal to x, and dv will be cosine of 2x to x. We differentiate to find du, and we integrate to find v. Then we put together in the parts formula, not forgetting the stuff that has gone before. So now my secondary integral in the parts formula is going to be uv minus the integral of v times du. So I'm going to have u times v minus the integral of v times du. So we just followed all the steps again. Step 0, it's not substitution. Step 1, assign parts. U is x and dv is cosine of 2x to x. Step 2, differentiate to find du and integrate to find v. Step 3, put things together into the parts formula. And then step 4, integrate your secondary integral. Our secondary integral has finally got something that's nice and simple. It's not parts again. I may be cruel, but I'm not a monster. Mostly. So now we just have to integrate our last integral. The integral of sine of 2x is minus 1/2 cosine of 2x. So I have to multiply it by the minus 1/2. Oh, that's right. We have a negative up here. I forgot that this first one was negative when I was panicking. They can't all be positive. So I got this term, minus 1/2 x squared cosine of 2x. This term here, it's plus 1, so I made it kind of easy on myself. And then minus 1/2, the integral of sine of 2x is minus 1/2 cosine of 2x. So minus 1/2, so multiply to get a plus 1/4 cosine of 2x. And now that we've integrated everything, we can finally tack on plus c. Integration by parts. That's a simple thing. How's everybody okay? Everybody thinking, dude, we can't have new things on Friday. That I respond, yes, it is a little bit. It is cruel, but in no way unusual. And since it's not a punishment, I can avoid that anyway. It's not, I don't care if it's cruel and unusual. Any questions? Comments? Let's another example. Step 0, not substitution. Step 1, assign parts. Making u the polynomial worked out last time, so let's continue that. Step 1, assign the parts. We made u the polynomial part again. Seemed to work out last time. Step 2, find du and v. Du is just going to be 1 to x. And v, when we integrate, always remember that over here we are integrating. That's why we're going to get a 1/5 e to the 5x. Step 3, drop your parts into the parts formula. We take uv. I keep picking things with constants that I want to split up, but I have to color code everything. Minus the integral of v times du. We look at our secondary integral, that'd be step 4, integrate the secondary integral. And it is indeed simpler than the one that we started with. Started with an x times e to the 5x, now we've got just e to the 5x. So we integrate our secondary integral. And we have a 1/5 x e to the 5x minus 1/5. The integral of e to the 5x is going to be a 1/5, and that's why we're going to end up with a 1/25 e to the 5x. Now that we've done all of our integrating, we can tack on our plus c. Box up our answer for shipping. Okay, right. Now you might think, dude, why didn't you lead with this one? It's so much simpler. And that's the reason that I didn't lead with this one, because it's so much simpler. Here's how we can complicate this. This might not be what a computer system returns to you as an answer. Notice that the two variable terms both have a factor of an e to the 5x in them. So sometimes rather than writing this e to the 5x over and over again, you'll see systems factor out e to the 5x and multiply by a polynomial 1 time, rather than take e to the 5x times a polynomial 2 times. So you might see an e to the 5x factored out. That would leave behind a 1/5 x minus 1/25. Notice that I'm leaving the plus c out of this factoring business. Just carry on the plus c at the end. Now notice I didn't put a box around this because this is most definitely not how you would see this displayed. If we're going to do this by factoring out the e to the 5x and multiply it by 1 polynomial, standard procedure would have that polynomial be written with integer coefficients. So not only would I factor out an e to the 5x, I would factor out the 1/25 as well. So you might see this this function written this way. At this point in your calculus career, I would prefer the first one. It's the one that you first came across. It was the first thing that you could tack a plus C onto. Just stop there. Do not do any algebra, because your algebra skills are only going to get you in trouble at this point. I'm not saying that your algebra skills are weak. No, that's exactly what I'm saying. I know you got A's in all your algebra classes, but algebra classes don't tell you enough. Getting an A in algebra class just means you're ready to move on. So don't do any unnecessary algebra unless you are sure of yourself. There is a good way when you're practicing to be sure of yourself. Wolfram Alpha. Wolfram Alpha like pops up and says, hey, it looks like you're doing some algebra. Would you like some help with that? It's like a little clippy, but Wolfram Alpha, and much more powerful. Also, I don't know why, when my hand is in this position, I can't just draw a line that goes straight up and down. See how it curves in? Over here, I completely reset my hand to draw this, but this one I was like, oh, I could do it from here. It's like, oh, no. But that's beside the point. Any questions? Is everybody okay? Just take the first thing that you've done, where you've done all your integration, put the plus C, that's your punctuation, put a box around it and say, I'm going to go with that. Let's do one more example. Here's an example where we're going to get our first piece of advice about how to make the choice of U and dV. Now you're going to go watch some videos from Professor YouTube, and they're going to give you some kind of mnemonic devices for how to choose between U and dV. But watch out. They're trying to program you with some friggin' flow chart. And that's bad for your development as a human being, except for the person who is actually a robot with a computer brain sent from the future to murder me at some predetermined time. I know who you are, and you will not get away with it. Not this time. But here we'll come across Leach's first rule of integration by parts. dV's got to be something you can integrate. First rule of parts, dV has to be something that you can integrate. Take this as your rule for how to use parts, and it will be the only rule that you need. So let's integrate x to the fifth natural log of x. This one should initially frighten you because that x squared led to 2 iterations of parts. X to the first had only 1 iteration of parts. X to the fifth, are we going to have 5 iterations of parts? Yes, that's exactly what's happening. This is going to be awful. And it's going to take until 9:30. I'm just kidding. That's not going to happen at all. Otherwise, I would have tried to cram this one in the last 5 minutes of class. I know when I started, there were 8 minutes of class left, but 8 minutes of class left when I'm running the class means there's only like 5 minutes to do a problem because I won't shut up. So the first step is deciding it's not substitution. There's nothing that looks like a substitution here. Derivative of natural log of x is 1 over x. I don't have an answer to the fourths. Not substitution. Plus, it's in the parts section. It's probably parts. Now, let's follow the same plan that we did last time. decide u is going to be the polynomial part. Let's make u equal to 5x. Sorry, u equal x to the fifth. And here we're going to run into our problem where why I brought up this first rule of parts. Because I write dv is natural log of x, and we're immediately stopped. Because we look at that and say, hang on, I don't know what the integral of natural log of x is. Or most of you don't know what the integral of natural log of x is. If you're thinking 1 over x, that's the wrong way. That's the derivative of natural log of x. But for the most part, at this point in your career, you don't know that the integral of natural log of x is x ln x minus x. It's obvious now that you think about it, right? You should, at this point, you'd be like, oh, yeah, clearly. And you're like, oh, what the heck is going on? No, clearly. So we can't do this. We can't use this deployment of u and dv because dv is not something we can integrate. So this is not how we're going to do parts. So this means we just have to do something else. The most important thing to do when you're trying to learn math is something. And we have an option here. This was a choice that we made. There's no rule that says this has to be a polynomial. Let's just switch the parts. Keep the dx on the dv side though. Now this is going to work out because I know the derivative of natural log of x. So one of our strategies when we see that we get when we see that we've written down a dv that we can't integrate, switch the parts. All we have to do is break things up by factors. So as long as we keep breaking things up by factors, we're going to be okay. Now we can differentiate to find du. And we can integrate to find v. Now that we've got the 4 parts, we can put things together in the parts formula, and hopefully our secondary integral will be better. And of course, I didn't leave myself enough space. So this was not our plan. I'm going to go uv minus the integral of v times du. So I've got this 1/6. I'm going to keep that on the outside because I like to factor out my constant factors. And then I'm going to have v times du. I have x to the 6th times 1 over x. And how much is that? Remember, clean things up as you go. I work at Domino's. That's one of the things they taught us. Clean as you go. Because we need to squeeze as much work out of you as possible. So this x to the 5th came from 1 over x times 1/6 x to the 6th. We just simplified it to an x to the 5th. And now our secondary integral is a small one. We have made our life easier by trading our messy integral for a clean integral. Any questions? This only seems like a lot to remember because it's a lot to remember. You have to remember all of it all the time in perfect detail. So that's not actually too much. Think of all the ridiculous things that you do remember. I mean, going way back to the beginning, like 7 times 8 is 56. All right. That's integration by parts. The integral of u dv is uv minus the integral of v du. That's going to do it for today. That's going to do it for this week. Everybody have a nice weekend. I'll see you all on Monday. Thanks for playing.